Section 3.2 is inverse functions and logarithms. So logarithm is a specific inverse function. It's the inverse function to the exponential function. So it kind of fits in as a special case of inverse functions. One of the first results we'll see here is what the derivative of the inverse of a function f of x actually is. We'll have a nice computational tool that pops out within this section, and then we'll move along to eventually talk about the derivative of a logarithm and the derivative of an exponential function. We'll also use derivatives of inverse functions, potentially in finding the derivative of inverse trig functions and things like that. But just in general, if we have an invertible function that's differentiable, so we have f, which is a differentiable function that has an inverse, f inverse, then we should be able to calculate its derivative. And we're going to see how to do that in a formula which follows. But before we can really talk about inverse functions, we should review a concept from a previous course. Typically, this is covered in algebra, and that's whether or not a function f is one-to-one. So, or injective is a term that gets used in more advanced math courses. So, an injective function or a one-to-one function. Students might remember this from an algebra course or otherwise, as you can check for one-to-one to see whether or not the function passes the horizontal line test. So in other words, horizontal lines through the sketch of a graph of a curve, and if those horizontal lines intersect the curve in at most one place each, then that function passes that horizontal line test and can be classified as one-to-one. But that really is only a heuristic. It's a nice way to envision that. The actual definition of one-to-one is given as follows. x1 equals x2 whenever f of x1 is equal to f of x2. So this is, the logic in this is a little confusing. Let me split the word or swap the word whenever with the implication symbol. The implication is actually going this way. What this thing is telling me is that if f of x1 is equal to f of x2, if my outputs for my functions are equal, then my inputs must have been equal, right? So whereas when we talked about whether or not a function was a function, it was actually a function, right? The definition of a function was a relation that implied this way. If we put the same inputs into this function, then they're gonna end up being equal to each other. The function always reliably gives us the same output for the same input, for equal inputs. So that was the definition of a function. However, the definition of one-to-one is the other direction. So if we have two outputs for our function, then one-to-one means they can only have ever come from the same place. So let's think about that in a quick example. I think this will help clarify a little further. So we know that the function y or f of x equals x squared is in fact a function, right? If I plug in an x value in here that's equal, if I said something like, well, maybe 2, or if I plugged in also 6/3, two numbers that are equal that I could plug into this function, when I'm done with the output and I simplify everything, oh, well, I'm going to get the same output. I'm going to get 4 in both cases once I do all the work. So that's the definition of a function coming to bear, right? However, this function f of x equals x squared is not one-to-one. And the reason we know this is we can look at something like f of -2 is equal to 4, right? -2 squared is 4, right? But that's also the same value that we get out of the function if we plug in 2. Okay, so now we have f of -2, or f of x1, equals f of x2, or f of 2 here. However, we don't have that -2 is equal to 2. Okay, so in other words, we've got two different inputs for the function that give the same output, which means it's no longer one-to-one. And of course, we remember what this function y equals x squared looks like as a graph. Well, it's a parabola opening upward. And we all know that a parabola is not going to pass the vertical line test, namely at a y value of 4, right? Because right here, a horizontal line test, a horizontal line at y equals 4 passes through this thing twice, and at many other places as well, but all we need is one counterexample to show that's the case. And we'll do some more examples with this as we progress with these definitions. So that's 1-to-1. It's very similar to the definition of a function, and that's why the horizontal line test and the vertical line test are what they are, more or less. Nice heuristics for that, but not really a proof of anything, but a good check for a quick analysis of things, and a nice way to think about it at least too. So f is a 1-to-1 function with domain A and range B. So if we assume this is the case, then the f is going to have an inverse function, f inverse, that has domain B and range A. So notice it just switches. So if the domain of f is A and the range is B, then the domain of its inverse, this is a map that goes backwards. It goes from B to A instead of A to B. Right? F goes from A to B, f inverse goes from B to A. And the reason that this definition looks so similar to the definition of a function is because when you read it in reverse, what it essentially tells you is that f inverse, right, if you reverse the logic of it, f inverse is a function, right? It will be a function if this is true. And we don't really need to dig into the logic of that, but that's why it looks so similar, one-to-one's definition as opposed to the definition of a function actually being a function, or a relation being a function. So furthermore, we define an inverse function, f inverse of y equal to x, as being equivalent to f of x equals y. So this is a really interesting dependency, right? We can't really talk about f inverse of y as a function without appealing to the function whose inverse we're interested in. So the way we define these inverse functions is this. So anytime we see f inverse of y equals x, we can immediately write down this rule to the right and use that to our advantage, wherever might be helpful. So we obviously have some cancellation equations, right? Remember that f inverse maps from B into A, and f maps from A into B, and they should do so in such a way that if we plug in an x to f, right? So x is some value in the set A, the domain of f, because we're first going to plug it into f. It's going to give us some output. But if we take f inverse of this output from f of x, then we should get back our original variable x, right? That's our cancellation, our inverse function cancellation, right? And we have one going the other way as well. It's very similar. If we pick up an x and b, and we do f of f inverse, notice how the roles have changed, the order of the composition has changed, then we get back the same value that we input. This is an identity or cancellation equation. Okay, and these are pretty useful to keep on hand as we work through problems involving inverse functions. So next up, we've got to determine whether or not a given function is 1-to-1. We've got two functions, I believe, or three, actually, I see here. Part A is the reciprocal function, f of x equals 1 over x. Remember, you could check this in a pretty reliable way by saying, by graphing y equals 1 over x and just checking to see that it actually does pass the horizontal line test. You can either use a graphing utility, like a graphing calculator, or you could sketch it by hand and more or less convince yourself. But we can actually go a little further, and I can make the claim that this function f is 1-to-1. So how can I be sure of that? So what I'll assume is this. I'll assume the other side of the implication. I'll assume that this is the case, f of x1 equals f of x2, for possibly different x1 and x2. And I want to make sure that I can deduce from that assumption that x1 is necessarily equal to x2. And that's how one of these proofs works. We don't always have to prove all of these things, but it's a pretty easy type of proof, and it's a good one to kind of maybe wrap your head around to practice this sort of logic and deeper mathematics. So I let f of x1 be equal to f of x2. Well, in this case, f of x is 1 over x. So f of x1 is 1 over x1. F of x2 is 1 over x2. Okay, so I get to move that far by writing this down. What I want to arrive at, I want to be able to prove that x1 is equal to x2. Well, it doesn't take a lot of work algebraically to actually do that. We just take the reciprocal of both sides of this equation, and we get the equivalent equation, x1 equals x2. So it followed really simply and quite quickly, with just one algebraic step moving from here to here, after we've written down the antecedent of our implication, which is f of x1 equals f of x2, we see that this implies x1 equals x2. Well, that's the definition of the function f being 1 to 1. So there we have it. We've implied that if f of x1 equals f of x2, then x1 must be x2 in the case of this function. So we see that it is 1 to 1, and we've proved that it's 1 to 1. Moreover, not just determined. And that's not necessary. I don't think there's any case where you're going to be required as a student in this Calc 1 course to prove that something's 1 to 1. But if you can, that's all the more power to you, right? Because you'll need to do that in later math courses. So we have g of x is equal to cosine of x. Now, is this 1 to 1? Well, we remember what the graph of cosine of x looks like, right? It's a sinusoidal wave, and of course, it's going to fail the horizontal line test. We can, at the line y equals 0, it's going to fail the horizontal line test. So, all we need is a single case of this thing, of this implication not holding, right? So in other words, of the f of x1 equals f of x2 case, not implying that the two inputs are the same. So we need two outputs of cosine that are equal, but came from two different inputs. And if we look at cosine is 0, well, we know cosine 0 is 1, and then a coterminal angle with 0 is 2 pi, right? But remember on the number line, 0 is here and 2 pi is out to the right somewhere. And so those two x values aren't equal. They just happen to be coterminal angles on some abstract thing called the unit circle. It's got nothing to do with this real number line right here. So what we see is that f of x is equal to f of x1 is equal to f of x2, but x1 is not equal to x2. So we found a single case, at least one case, where the condition doesn't hold, right? And this means that the function's not 1 to 1. It only has to fail the horizontal line test in one spot, is another way of thinking about that, or for one horizontal line. And this one, in fact, does so. So now we look at a table, right? Some functions are represented as a table. And what we do when we scan one of these is we look through and say, okay, what I'm mostly worried about is a place where my output values are equal. And I see that we have two output values of 2.0. If this function is going to be 1 to 1, then the x values corresponding to those equal y values need to be the same. But the x value for the first one's 2, and for the second one is 6. 2 is not equal to 6. So what we have is f of x1 is equal to f of x2, but x1 is not equal to x2. So we've got another single instance of our implication for 1 to 1 not holding, and that's enough for this function not to be 1 to 1. It only has to fail in one place for it to not be 1 to 1. So those are some examples of assessing whether or not a function is 1 to 1. The first one, we just had the benefit of actually being able to prove that it's 1 to 1. Sometimes those can be tricky proofs. Again, we don't really need to worry about it. Note also, though, that these are actually proofs as well. Giving a counterexample to show that something does not meet a condition is actually proof that it's not, it doesn't have that property. It doesn't have the property of 1 to 1 in this case. So moving on, what we're really interested in is, of course, calculus on inverse functions. Okay, so if f is 1 to 1 and continuous on an interval, then it turns out that its function f inverse is also continuous. And that's probably worth looking into the proof of. I'll keep the video shorter by not digging into it. The textbook, of course, will cover those details, and perhaps we could explore that in a meeting at some time. But second to that, following up, and we need this fact actually in the actual proof of the next theorem, so that's why it appears here. It's also just a good thing to know, and it should make sense. A 1 to 1 function that's continuous, well, if it's 1 to 1, it's going to have an inverse. And if it was continuous, its inverse function should be continuous too. And that's, we'll see maybe an argument graphically, again, just another heuristic for why an inverse function should be continuous if the given function f was continuous to begin with. So moving on, now let's get to this next important theorem. If f is a 1 to 1 indifferentiable function with inverse f inverse, and we have that f of f inverse of a is not equal to 0, then its inverse function is differentiable at that value a, and moreover, it's given by this formula here. Okay, so this is sort of our key piece of work, right? And what we'll extend this to is we'll later extend this to, and we'll just do it here and probably leave it in the notes, but this extends to any value x. If a function f is differentiable for certain values of x, then and it's 1-to-1, so it has an inverse, f inverse, then we can calculate its inverse's derivative as a function of x, and that's going to look like this. Really, all that's happening is I'm changing any instance of a out for the variable x, right? So we can, as we always have, or as we commonly do, express the derivative as a function of x. Okay. Naturally, that's the case. But what should be noted here is that it's important that we go in this order. Remember when we define the derivative of a function at a value a, well, that's where we started. And then we said, well, if a function f is differentiable for all x values in an interval around some number a, or for some given interval, then f prime of x for x in that interval can be calculated as such, and is, we call f differentiable on that interval or on its domain, if that happens to be all the numbers in its domain, which commonly is the case for a lot of functions we deal with. So the proof that's below, or the derivation below, is not actually a proof. It's just another sort of intuitive look at this situation. If we happen to know beforehand that f inverse was differentiable, well, then we could proceed in this fashion. But what I like this derivation as opposed to the actual proof of this and derivation of this theorem, because it's a little bit more intuitive and it uses some tools that we've dealt with in the past. The book, of course, walks through the proper derivation of this formula, and that's a good thing to take a look at. But here I'm just going to forego that and give you this nice tool for, in case you ever forgot what the formula for the derivative of an inverse function is, this is a nice way to go about finding it. So what I write down first is y equals f inverse of x. So I've got an inverse function, f inverse of x, and it's, of course, it's the inverse of the function f. But what I know about my relation for inverses, or the definition of this inverse, if y is equal to f inverse of x, then f of y is equal to x, right? In other words, I apply f to both sides of this equation, and by my cancellations, I get that f cancels on the right with f of f inverse by the cancellation law, and then on the left-hand side, I'm just left with f of y. So that's how we have f of y is equal to x. And now we just make a simple move here. We take the derivative with respect to x of both sides, right? On the right-hand side, that's particularly easy. It's the derivative with respect to x of x. So that derivative is 1. It's not implicit. X is an explicit function of x, right? It's literally the identity function, right? So the derivative of that is just 1. Okay, remember this is ddt of x, then we'd have 1 times dx dt for an implicit derivative. But we're not in that realm on that side, at least. When I take the derivative with respect to x of f of y, well, now I realize I have an outer function f, so that's going to be f prime of y, the inner function, right? And the chain rule says times the inner function's derivative. So I take ddx of y, that's dy dx, or y prime. So the chain rule or implicit differentiation gives me this. Right? So y prime comes out of that. Now if I solve for y prime, because after all, if I'm looking for the derivative of f inverse of x, well, y prime is that derivative. I can come down here and say y prime is equal to 1 over f prime of y. And then I can recall that, well, y is equal to f inverse of x. So I get f prime of y, well, y is f inverse of x. So it's f prime of f inverse of x in that denominator. And there we have the formula that we were proposing up here, only in terms of a, but the more general one in terms of x is given here. Again, this is not the proper proof for this moment, but I think it's an easier tool. It's a better tool to see and have around in case you did ever forget the derivative of the inverse function. This is just a summary of what we came up with, right? We found y prime, and y prime is literally the derivative of f inverse of x. So that tells us that ddx of f inverse of x is given by this formula here. So it's a nice little intuitive rule to just sort of see how it comes about in one sense, and to also maybe help remember this if it's ever forgotten in the future. So let's get to work with a more explicit function, right? Let's do something less abstract. Again, let's see, we're given f of x equals root x minus 2, and we're asked to do a series of things with this function. The first is to show that f is 1 to 1. We're going to show that f is 1 to 1. This is in other words, prove that f is 1 to 1. So remember, to prove that, you start with f of x1 equals f of x2. And then what you need to arrive at is you need to show that for general x1 and x2, I can't put numbers here. I put two different variables, x1 and x2. I need to be able to show just from my function's definition alone and some algebra that x1 is necessarily equal to x2. And that's what ensues in this, right? So from this line, I know that f is the root x minus 2. So I do root x1 minus 2 and root x2 minus 2, just because that's what f does to those two variables. They're set equal to each other because that's what I started with in this identity, right? If I square both sides, I get this line. If I add 2 to both sides, I arrive at this line. And what we've done is we've just shown that f of x1 equals f of x2 implies that x1 equals x2. And again, I didn't use any numbers other than x1 and x2. These are arbitrary variables in the domain of the function. That's the only thing I needed to stipulate about x1 and x2. I didn't let them be two specific numbers because that would only prove it for those two specific numbers. So nonetheless, yeah, we have that f is 1 to 1. We've demonstrated that. There's another proof of that. And that's really as easy as those proofs can be. It's just you write this down, you write down what that means, you do algebra, and hopefully arrive at x1 equals x2. If you don't arrive at that, then it's possible the function's not 1 to 1, or maybe there's a trick that you just need to work out. Part B, calculate f inverse of x and state the domain and range of f inverse. So remember how to calculate the inverse of a given function. This is practical stuff from college algebra, right? What you do is you write down your function, y equals root x minus 2. However, instead of in that form, you swap the role of the variables. So I've swapped x and y. So now I have x equals a function of y minus 2. And what you do to find the inverse function is you solve for this y variable. And when you're done, whatever you arrive at is some function of x. And in this case, here's one intermediate step, but ultimately we end up with y equals x squared plus 2. So our inverse function, based on this calculation, f inverse of x is equal to x squared plus 2. All right, that's a old material from a college algebra course. What we should remember now is they ask us about the domain of f inverse and the range of f inverse. If I look at this function, I might not be very careful about that. I look at that and see a polynomial, and I'll say, well, that domain is all reals. And then I look at it thinking of the range. The range is a little bit easier to detect, and we were correct about that one. The smallest this function will ever be in terms of values is 2, and that's when x is 0. And it'll go on from 2 upward towards infinity. So the range of this function is dependably, we can observe that and get that, right? I mean, unless the domain of f itself was restricted for some other reason, it's exactly what it appears to be. However, the domain of this has to go along with the range of this function, right? So, where I could say it's any real number because it's a polynomial. Well, this function's the inverse of this one. So as such, it needs to match up with my original function. So remember, the domain of this function is the range of this function. So the domain of the inverse is the range of the initial function, and vice versa. The range of the inverse is the domain of the initial function. So if I look here, I realize that, well, okay, the range of this function, we can get as low as an output of 0, and that's when x is equal to 2. And after that, x has got to be greater than 2 because I can't put a negative into a, oh, sorry, I'm going towards the range. So the smallest this function can be is 0. The output, so the range of f is 0, and then upward. Everything that comes out of this is positive after that. So 0 to infinity. All right, so that's how we get the range of f, which then tells me immediately what the domain of f inverse is. So the inverse function inherits its domain as the range of the initial function. And same for its range. Typically, its range you can just read straight from the function that you calculated here. So there we go. But these identities, domain and range, the way they flip for each function, will always hold, right? That's a fact from the first couple of theorems we looked at. Next up, they ask us to calculate f inverse prime of the number 8. So this problem is interesting. They're giving us some a couple ways to work around this and confirm that our formula makes sense, right? So why, I don't need that formula at this point. I don't need the formula on the previous page at this point for one simple reason, right? I don't need all this clunky calculation for the simple reason that I already know what my inverse function is. I found it here. If I want the derivative of that inverse function, I'll just take the derivative of this function. And when I do that, I get f inverse prime, its derivative is 2x. It's just the power rule, right? X squared plus 2 has derivative 2x. So that's what I go with, right? And that's the easiest way to get there. So if you've calculated the inverse, there's no reason to run it through the big formula. You could just calculate its derivative if you're looking for that next. And of course, well, f inverse prime of x is 2x. And if I just plug in 8 for x, then I have 2 times 8, and I get an output of 16. But just to confirm that this formula is working on the previous page, we can run it through using the reciprocal formula. Again, it's not necessary that we do this unless the problem explicitly asks us to, but for the sake of learning about this stuff and convincing ourselves that this formula seems to be working, well, this is, we'll run through this calculation. So f inverse prime of 8, on the other hand, according to our formula, is 1 over f prime of f inverse of, in this case, our value a is 8. So that's what we're going to plug into this. So first things first, we evaluate f inverse of 8. Well, f inverse of 8 is 8 squared plus 2. Well, 8 squared plus 2 is 64 plus 2 is 66. Now I have f prime of 66. Well, what is f prime? Well, I go all the way up to the top, kind of glossed over that, didn't really talk about it, but we can calculate it up here pretty quickly. This is x minus 2 collectively to the power of 1/2. Take its derivative, 1/2 comes down. Everything's to the power of negative 1/2. The chain rule of the inside of this just gives us a 1. It's all times 1, so we don't really need to write that. So there's f prime of x as this rule. So we'll apply that to the number 66 down here. We have 66 minus 2 to the negative 1/2 power, and all that's times 1/2. So what comes out of this? That's 64 to the negative 1/2. Well, 64 to the negative 1/2 is 1/8. And then 1/2 times 1/8 is 1 over 16. But all of this takes place in a denominator. So 1 over 16 gives us 16. So a little bit of a agile arithmetic or algebra going on there. But we see that in the end, our formula does appear to be working. This is just confirmation that it doesn't prove the formula is valid for all cases. We would already see that in the textbook, but we just get to see here that this works either way. Right? So lastly, they ask us to sketch the graph of f and f inverse on the same axes. And this one I want to do just to show, just to remind students of graphically what how these functions behave, right? So f of x is root x minus 2. F inverse of x is x squared plus 2. So f of x is root x minus 2. That's this curve right here, right? As labeled y equals root x minus 2. F inverse of x is the curve, and let me label that with a y equals f of x scheme, and that's x squared plus 2. Okay, so remember that inverse functions have this interesting relationship to each other. If I look at the line y equals x, and you always consider that line in terms of inverses, if I were to fold the plane or the graph along this line, right, fold diagonally across the plane, and if I drew this very well and paid very close attention to scale, maybe you go to Desmos and look at this, what I would see is that the blue curve would land exactly on the red curve. They would match up as we reflected or folded across the line y equals x. Okay, namely what we would see is that x and y swap roles. And that's interesting because that's how we calculated it in the first place, right? We swap the roles of x and y and then solve for the other variable. And what you see here is that these xy coordinate pairs, here's the point 2, 0. Well, it has a partner point over here, 0, 2. X and y have flipped to y and x, right? Similarly, 3, 1 flips to 1, 3. X and y is flipped to y and x. And that's really just a nice, yet another way to see inverse functions and a nice property that they have. So if you know the graph of one of them, you can easily reflect and sketch the graph of the other one. And you can literally do that by just knowing a couple points on the other curve and the general shape of it, and you get a pretty accurate representation of the other one, or at least one that's just as accurate as the initial function's graph. So yeah, we'll keep that in hand. When we move to logarithms and exponential functions, what we'll see is something very similar to that situation. So, and that'll help us graph the graph of a logarithm. So find f inverse prime of 2 for the function f of x equals x cubed plus 3 sine x plus 2 cosine x. So, all right, this is just a straight evaluation. We don't have to do a whole lot of algebra involved with this. We just need to go through and calculate this thing. So I'm just going to use the formula directly. So I need to find f prime of f inverse of 2 and take the reciprocal of that. Now, well, first things first, f prime of x, well, power rule and then derivatives of trigonometric functions give me the following, right? The constants are just hanging out in front of those trig functions. And then f inverse of 2 equals x. So what I'm interested in doing here is figuring out what's the output of this function, right? So that this is not exactly explicit in the moment, right? I have f inverse of 2 is equal to x. So what I need to do with that, right? The key step here was to say that this is equal to x, and then what I'll do beyond that is see that I can write this as its inverse relation 2 equals f of x, and now that's something I can work with because this creates an equation for me. 2 is equal to that equation. And it just so happens when we go to solve for this, it can look pretty fierce, right? But we kind of can just guess and check a solution to this. I look up here, I realize, well, 0 here gives me a 0. 0 here gives me a 0. And plugging in 0 here gives me 2 times 1, which is a 2. And then 0 plus 2 times 1 is 2. It's not the best way to go about solving an equation, but sometimes guess and check is all you've got. There's no standard method for finding roots or certain values of an equation like this, right? So that's pretty difficult potentially. Maybe a graphing utility could come in handy. Questions shouldn't be too involved regarding that situation in the homework or examples. So it looks like x equals 0 will give me an output of 2. So in other words, f inverse of 2 is equal to 0. And that's the key thing I needed. F inverse of 2 needs to be 0 here. So then I have f prime of 0. Well, what's f prime? This is f prime. So I'm going to evaluate this with x equals 0. And that's what's going on down here. Right? And what we get out of that, the only surviving term is 3 times cosine 0, because cosine 0 is 1. 3 times 1 is 3, and you have 1 over 3 ultimately. So there's a little nasty little trick in there. The other option would have been possibly, and we'll see why it wouldn't work, is to go here and say, okay, well, how about I just calculate what f inverse is as a function of x? Well, good luck with that, right? Because what do? You take each of these variables for x, you swap them with y, and you write all of this as being equal to x over here on the side, right? Equal to x here, and then you try to solve for y. Well, good luck with that, right? That's going to be a really difficult scenario. So we don't have to know the inverse function. We just have to be able to evaluate it at a specific point if we're looking for the derivative at a specific point. So there will be a few problems like that, and I do think that it's really a matter of guess and check here. It should be somewhat obvious which numbers you should try. 0, 1, -1, those are some favorites to go plugging into things, but use your senses and intuition to kind of figure out what one of these evaluations might be. Or if the function's just straight up invertible, find its inverse. So this brings us into logarithmic functions now, right? So remember that the logarithmic function of base a, so a is a positive number that's not equal to 1. We don't use base 1 for logarithms, just in the same way that we don't use base 1 for exponential functions. They're just not interesting, right? Base 1, well, 1 raised to a power is just 1, so we don't talk about that function. So a is not equal to 1. And log base a of x equals y. Remember that we define this as a to the y is equal to x. Remembering this equivalence, this definition for logarithms is pretty critical, right? This will get you through a lot of mix-ups and a lot of difficulties in dealing with exponential and logarithmic functions in general. It'll help evaluate logarithmic functions if you're not sure about, maybe an evaluation you're trying to do with one. It could even help you with solving logarithmic equations, and those are going to come up from time to time. So remember the laws of logarithms. We had 3 main laws. Log base a of some numbers a times b, where a and b are both positive, is equal to log base a of a plus log base a of b. Similarly, log base a of a over b is the difference log a of a minus log a of b. And then log a of a to the c is equal to c times log a of a. Right? This is that power rule that lets us bring down an exponent inside the logarithm down as a multiple of the logarithm. Now, most of these are really nicely proven through basically through the exponential definition of the logarithm. We show that typically in an algebra class by converting this side into an exponential equation or expression, and then arriving at this side through laws of exponents. But we don't really need to review that in order to remember the laws of logarithms. And lastly, we have a change of base formula for logarithms. So log base b of x, again, for real numbers a and b that are not 0, so greater than 0. And also, we should also say that a and b are not equal to 1, right? Because those are not interesting log bases. So if this were the case, remember we can do a change of base formula so that log base a of x over log base a of b, well, we're able to change from log base b to an expression involving log base a. All right, now in calculus and maybe an analysis of functions, what we might be interested in is what this really means about logarithms and their graphs. So note that log base a of b, a and b are some fixed numbers, right? They're just not 0 and they're not 1. They're positive and they're not 1. So log base a of b being a constant, well, this is a function of x, as is this. What it looks like here is I'm going to factor log base a of x off of this numerator out to the right. And I'm going to leave a 1 in the numerator and then times that what was in the numerator. Again, if we simplified this expression, we get what we have on the left over here. So when I do that, what I see is the following. This tells me something interesting. This is 1 over a number, 1 over some constant. Of course, it's based on a and b in the logarithm. But it tells me that log base b of x is a multiple of log base a of x. And that's true for any a and b, so for any logarithmic bases. So this convinces me that just like exponential functions, it doesn't matter how different the base is, they're only different from each other by a scalar factor, right? And this is that scalar factor, by a constant factor, by some multiple. Remember that exponential graphs are either stretched or compressed vertically, and that's exactly the same situation for logarithms. They're either stretched or compressed vertically, and the way you do that is through a multiple like this times the other function. So all logarithmic graphs more or less look the same, just like exponential graphs. Furthermore, that sort of conjecture is backed up by what we see below. Oh, here, by the way, is a quick example. Log base 2 of x, change of base formula. There's the new base will be 3, right? It's 3, which is down here. So a is 3 and b is 2 in this case. So we end up with log base 3 of 2 in this position. And that's times log base 3 of x. So what I see here is that this is a number, of course, right? We could get some calculator approximation of that. And what it tells me is that log base 3 of x is only different from log base 2 of x by some constant factor. It's either stretched or compressed, right? So that's a further example there. Now, a quick graph of this situation. Remember logarithmic function or exponential functions graphs. Y equals a to the x has the following graph. When x is 0, a to the x is a to the 0, so a is 1. Of course, or sorry, so the output is 1, y is 1. Remember that our base is greater than 1. This would be something like 2 to the x or 5 to the x or e to the x even. Pi to the x would work as well, whatever. Anything greater than 1. Now, if y equals log base a of x, well, that's the inverse function of y equals a to the x. Well, remember, we just draw our line y equals x, and then we reflect this function's, the graph of this function across y equals x to arrive at the graph of this function. So we sort of immediately and somewhat for free get the graph of y equals log base a of x. So we see some very important things about the domain of log base a of x and the range of it, right? The domain of e to the x was all reals. So the range of y equals log base a, range of a to the x, y equals a to the x is all real. So the same thing for e to the x, but any general a to the x, that's for a is greater than 1. However, when we look at y equals log base a of x, its range is all reals. So the domain of this function, the exponential, is all reals, and the range of the logarithmic function is all reals. So good to know, right? How if we look at the range of the exponential function, that's from 0 to infinity, and that's open 0. It doesn't include 0, right? If we look at the domain of logarithm, which matches the range of the exponential function, then we have the same. We go from 0, non-inclusive, to the right towards positive infinity. So just some nice things that match up with the facts that were listed previously. And that's a quick way to get sketch the graph of log base a of x, or y equals log base a of x. So lastly, what we'll consider are limits of logarithmic functions. We'll need that in the next section. I believe we're going to start talking about the derivatives of exponential and logarithmic functions. They're sort of coupled in a way that we needed all of this background material before we get there. So here, if we have a is greater than 1, then the limit as x approaches infinity of log base a of x is equal to infinity. Well, we could see that graphically, right? And again, it's not a proof, but it's a pretty good graph of it. This thing's going to continue to attain any value along the y-axis that we need to by moving sufficiently out to the right on the x-axis to get there. I did sketch a quick little proof to go with it, right? So if we let m be greater than 0, remember this is the game. We're going to prove this one. So if m is greater than 0, we're thinking of it as give me any large number you can come up with. So I'm letting m be greater than 0. It's going to stand in place for any large number you can come up with. My proof is going to provide a recipe for finding x values that will make my log base a of that x larger than this m. And that's how we show that something has a limit that approaches infinity as x goes to infinity, right? So we observe that for n greater than or equal to a to the n plus 1. So in other words, I found a number. Here's a number. If I pick any number that's bigger than that number, then I'm guaranteed the following. Check this out. We say log base a of n is greater than or equal to log base a of a to the n plus 1. Well, maybe we need to prove that logarithm's an increasing function. We could come around to that eventually, but this is suitable enough for now. Log base a of a to the n plus 1. Well, use the power law for this exponent. It comes down as a product, log base a of a. Well, log base a of a, what is that equal to? Well, remember how to analyze or evaluate a logarithm. A to what power is equal to a? Well, a to the first power is equal to a. So this log base a of a evaluates to 1. So this is n plus 1 times 1. So there we go. n plus 1 times 1 is obviously larger than m. So I've just provided a recipe. If there's any large number we can think of, m, capital M, well then based on that capital M, I can create a number. I take the base of the logarithm, raise it to the n plus 1 power, for any number n that's bigger than that, well, log base a of that number is bigger than n. So I know that I can grow my function to be larger than this proposed large value. And since I can do that for any m value, that means that this thing is always going to hold, right? And I've just established that the limit as x approaches infinity of log base a of x is equal to infinity, right? Done that for an arbitrary m, and for all n values that are greater than this, we can kind of think of those maybe as x values now. N is playing the role of x. Yeah, we can find a value that's larger than that m, or we can get logarithm to evaluate to a number that's larger than m. And we do a similar proof for the other side if we wanted to. The log base a of x as x approaches 0, the limit as x approaches 0 from the right of log base a of x is negative infinity. Again, the proof's nice to be able to do. You're not really ever going to be accountable for that in this course. Think of this: as we move to the right of 0, as we move to 0 from the right, we're moving leftward, right? This function, log base a of x, is approaching negative infinity. So yeah, we see quite handily from the graph both of these results here. I just thought this was a nice place to do a quick attempt at another proof for one of these limits, right? Just a sketch of it, and because a lot of students will have this in their future. They'll have to write proofs like this. Again, this isn't totally formal, but it's getting pretty close. So with these tools in hand, we can now evaluate limits of functions involving logarithms, natural log or otherwise. Remember, ln is log base e. E is the number 2.71, so on, right? So a is greater than 1 for log base e. So both of these rules apply if we happen to be able to use them. And we're going to kind of angle for that, right? So as x goes to infinity, the limit as x goes to infinity, of natural log of 1 plus x squared. Well, 1 plus x squared as x goes to infinity goes to infinity. And the natural log of something that goes to infinity is also going to infinity. So here we have that case. Similarly, on the right, minus the natural log of 1 plus x. Right? Well, 1 plus x goes to infinity as x goes to infinity, and natural log of something going to infinity also goes to infinity. So you could do some u substitutions here if you wanted to really kind of do a clean analysis of that. But what we see right now is that we have this indeterminate case, right? This means nothing. I put it in quotations and I put a question mark because I'm wondering, well, what does it mean? What are we going to do with this? Infinity minus infinity. We don't get 0 from that. We're not guaranteed that, right? Never, ever do algebra with infinity. It might work out in your favor. You might get lucky and get it right, but it's in no way a derivation or a proof. It might just be a lucky heuristic at times, but oftentimes it's wrong. It's probably wrong just as often as it's right. So nonetheless, let's see what we might be able to do. Well, remember we have log of something minus log of something else. These logs are the same base. If I go back a page, I remember a log law that helps me out here. Same base, log base a of a minus log base a of b. I can write them as a single log with a over b. You've probably done some exercises like this back in algebra and possibly forgotten it, but here's a nice refresher for it. Right, so this is what we've got within the brackets or the argument of our limit. We're going to have natural log of this argument divided by this argument. So we form this quotient in here, 1 plus x squared over 1 plus x. Okay, we have the natural log of that. Now we can think a little bit more about what's going on. This is still going to infinity as x goes to infinity. This is still going to infinity as x goes to infinity. So we're still a little bit out of luck here. So we have to think a little bit more deeply about this. So what I want to do is maybe pick up this quotient here and consider its limit all by itself. So I'm going to name this thing u. I'm going to let u be equal to the argument inside of natural log here. And I want to make, so I've claimed down here that this thing goes to infinity as x goes to infinity. But the proof or the step to get there is the following. If I take the limit as x goes to infinity of 1 plus x squared over 1 plus x, remember how to assess something like this. Of course, you could use the numerator's got a higher degree than the denominator, so this thing's running off to infinity. That's probably fair enough and practical enough to be thorough. Some cases where it's ambiguous or harder to tell, remember you find the dominant term in the denominator, in other words, the leading degree term in the denominator. In this case, it's x, and you divide the top by x and the bottom by x, or multiply by 1 over x. And what we do is we simplify this. We see in the numerator, we have 1 over x, and we have x squared over x, which is x. In the denominator, we have 1 over x and plus 1. So here we go for that. So what we see is in the denominator, this is 0 plus 1 as x goes to infinity. So the denominator is approaching 1. However, the numerator is 0 plus something approaching infinity. X is approaching infinity. So we have this thing is approaching positive infinity overall. Again, you don't always need to show this elaborately, but in case you ever get stuck and aren't sure, or the functions are harder than just polynomials, this is a good tool to have on hand. So now we know that this whole thing goes to infinity as x goes to infinity. And now we can appeal to the theorem above. You say, well, okay, as the argument of logarithm goes to infinity, well, the logarithm is going to go to infinity. And that's exactly what happens here. So this thing here, which was equal to that, right? We know that u is going to infinity, right, as x goes to infinity. So we swapped everything out completely to make it look exactly like this up here. Only the log base is e instead of a in our case, and e is greater than 1, so it still fits the rules above. And we end up with positive infinity coming out of that. So I'm doing a lot of the legwork to talk about all the justification for it. Most of these steps should be somewhere in there. Maybe this one, if you did a shortcut to here, that'd be just fine, right? But knowing how to do this if you're not sure is always really good. The substitution, that's better than saying something like this whole expression is equal to natural log of infinity. If you write something like natural log of infinity, well, now you're doing algebra with infinity, and that's just no good. It's of course in this case you'll end up saying, okay, it's infinity, and the heuristic works, but it's not sound. It's not good to do algebra with infinity, because look what kind of mistakes it could lead you to. And so you really want to avoid that. I mark off for that. I don't want to see natural log of infinity pretty much ever, right? I'd rather see this. So we don't touch infinity, right? Limits handle infinity. Okay, lastly, limit as x approaches 0 of log base 10 of tangent squared of x. Okay, so our outer function inside here, or our outer function is log base 10. What we're really interested in is, okay, what is going on in log's argument? Is it going to 0 from the right? Is it going to infinity? Is it going to some fixed number? If it's going to something like, I don't know, 1, then that's easy. If tangent squared of x is going to 1 as x goes to 0, well then log base 10 of 1 is the output for this. However, this one isn't going to some nice constant like 1. What we see is that as x goes to 0, the limit as x goes to 0 of tangent squared of x, well, we can consider it as the square of the limit as x goes to 0 of tangent of x, by exponential power limit law, right? And tangent of x, well, as x goes to 0, tangent x goes to 0, right? You can look at the graph and remember that tangent x is sine x over cosine x. Nonetheless, we realize, okay, that can be evaluated directly, and it's 0. And here's one very subtle aspect of this. If we approach 0 from the left, tangent of x is going to approach 0 from the left. It's going to be little negative numbers, right? But if we're squaring all those little negative numbers, well, they're going to come out to be positive. If we approach 0 from the right, well, our limit tangent x as x approaches 0 is going to approach 0 from the right as well. So what we're getting sort of, I wrote 0 squared here just to sort of show that it doesn't matter which side of 0 we approach tangent of x from, or which side we approach 0 from for tangent of x squared, we're always going to approach from the positive side of 0. And that's really important, because if we look up here, that needs to be the case. Whatever's in the argument of logarithm needs to approach 0 from the right in order for this to be true. So since we have that down below, I'll just wrap up the conclusion of this. We see that, okay, I'll make a swap here. U equals tangent squared x. U approaches 0 from the right as x approaches 0. Okay? We've kind of affirm that from up above. And now I can just replace tangent squared of x and x with u as follows, right? And u is approaching 0 from the right now. So we made that correction down here. And we have log base 10 of u. And that's exactly what the rule looks like above us. So we get negative infinity out of that. So why, again, did we have to be so careful about that? Well, let's look at the graph just to confirm. Look at log base a of x, right? Log a is 10 in this case, right? And for our example's case, it looks more or less exactly like this shape, maybe squashed or stretched or whatever, by some amount. If x approaches 0 from the right, well, then things are well defined. And yes, we're going to approach negative infinity. We're going to move downward. Can we approach 0 from the left and get a sensible limit out of the logarithmic curve? No, there's no red curve over here. It's undefined over here. So had we done this for just tangent of x instead of tangent squared of x, we would have to say it's undefined because the two-sided limit of tangent of x, it doesn't approach 0. Well, it doesn't approach 0 from the right. It approaches it from the right and from the left. So we wouldn't get this nice little extra piece that we need here. So we'd be undefined on one side and negative infinity on the other, which is technically also undefined, but really we'd have to say if there wasn't a square here, we'd have to say d and e instead of negative infinity. It just simply doesn't exist. It's like asking, what's the limit as x approaches negative 2 of log base a of x? Well, here's negative 2. There's no red curve to be found anywhere near this, right? There's a gap here. There's nothing over here. So we couldn't evaluate that. That's just d and e, right? It does not exist in that case. So there we have it. A review of logarithms, log laws, some calculus for inverse functions, and at least the limits for logarithmic functions. I'm fairly certain that in the next section, we're going to talk about the derivatives of logarithms, and I think probably also the derivatives of inverse trigonometric functions.